Good evening, everybody. Welcome to Monday night in the lab. Been noticing also on the discussion groups, folks noticing and asking about why is the reactance of the open stub reactive, capacitive specifically, when we're expecting it to be at an impedance minimum 0J0. After all, we're working with a shorted stub, open stub, and on the other end of it, a quarter wavelength away, it should be a short, so why aren't we seeing that? In one of my answers to a different section, not Monday nights, I commented with a frequency that defines the impedance of a coax at a given length and frequency. Now that answer was correct, but it was incomplete at best and probably represents only about 10% of the reason why we're seeing this happen. Far more important and far more influential, the real culprit is coax number one. And that's what's causing these impedance issues here. Let me demonstrate that to you by going into tuning mode. We start at 30 inches. We can see that our impedance over here is certainly capacitive, not over here at 0J0 where we would expect. Now, this stub is 9 inches long. So it's a quarter wave at the frequency 216.3 megahertz. This piece of coax over here is 30 inches long, and if you divide 30 by 9, you end up with 3.3, which means in terms of lambda, this is 3.3 lambda over 4, because this is lambda over 4, quarter wavelength. Well, we can actually subtract 2 from that because our impedance repeats every 2 lambda over 4, every half wavelength. So this actually ends up being 1.3 lambda over 4 long, just a little over a quarter wavelength long. And we can see we're right in between 27 and 36 inches, 27 inches being 3 lambda over 4, and 36 inches being 1 lambda. So what happens if I start making this longer and I go up in 1-inch increments? Well, as you can see, my reactance starts reducing, getting closer to J0 till I get to 36 inches. And lo and behold, I am about as on it as I can be. I'm at 1 ohm in 0.158 J, positive, slightly inductive, but for this case, it's non-reactive. Okay, that's fine. Let's go the other direction now. Let's go back from 36, back through 30 toward 27, which would be 3 lambda over 4. And so now we're at a high impedance point. And that would be what we would expect, because with this being an open and a high impedance point, a quarter wavelength later, we're at a low impedance point. So we're at a low impedance point here, and if this is an odd quarter wavelength long, then my low impedance gets transformed to a high impedance, which is exactly what we're seeing. So this is working exactly as we would expect a transmission line to behave, right around a quarter wavelength. So what are the rules of the road here? How do these things behave, and what can we expect? Well, let me reset this and get this back over to 36 to start the explanation. When we make C1 longer, and we're going from an even multiple of quarter waves to an odd multiple, and we make C1 longer, we are contributing inductance. The reactance is greater than 0. So we can see that just by making this longer. And we can see we're heading higher and higher in impedance, and we're certainly and clearly inductive. If we make C1 shorter and we start from the odd side and we go back, we're just backtracking on ourselves, right? And we're still in this inductive range. So far, so good. If we're going to make C1 continue to make it shorter, and we're going to go from this even point to the odd point, now we're going to be capacitive. Our reactance is going to be less than 0, and we can see on the marker that it certainly is. Until we get to the odd point. And we're just barely in there because we're capacitive. If I were to move it one more time, we flip into the inductive side. And this is because this is determined by tangent theta. And we've got that asymptotic relationship where it starts negative, flips, goes up through positive, drops asymptotically again, goes back up, flips up the other way. So as C1 goes longer, from the even multiples to the odd multiples, when we start at this point and we go this way, we're inductive. We start at this point and we shorten it, we're capacitive. From the even point. If we start at the odd point and we go toward even by making it shorter, we're inductive. If we go toward even by making it longer, we're capacitive. That's just the Smith chart helping us out here and showing us what's going on. One other thing worth seeing here, and this is really kind of trippy. What do you think is going to happen if I set this to 0? If I set the length of C1 to 0 and say it's not even there, coax 1 is not even there. Well, check this out. This is more or less our ideal response. With this coax being 0, we have our open stub, quarter wave length later. It's a short. There's no transformation going on because this, for all purposes, is gone. So we would see that impedance low, and sure enough, we do. At our quarter wave frequency, we see a impedance of 0.2 plus J 0.031. No reactance, no resistance. And the only way we get any impedance changes out of this is by changing the frequency. That's what causes us now to travel around this circle. Oops, do it this way. Is by changing the frequency. And so now you see the impedance changes, but we are going to follow this ideal circle because now we're holding the length constant of the stub. And coax 1 is not changing. It's 0. Stub is staying constant. So then we just make the circle around there of the impedances through the frequencies, and we eventually get to this other side where we get to pretty dang close. That was our maximum. So somewhere right around in there. So I wanted to point that out to you. That's how that works. That's why that was reactive. Bottom line is that it was reactive because we had 30 inches of coax acting as an impedance transformer. Come on. Wouldn't you know, ADS chose this moment to act up. Never does for me. Anyway, Point being 30 inches, we end up with the 1.3 lambda, we end up over here in this capacitive region because of the influence of this coax. Any questions, you know how to get a hold of me. Texting, email, we can talk on Zoom, whatever you like. And that's it. Thank you much. Talk to you later.